So the first thing I'm going to do is finish what I was doing earlier, which is I was explaining the MATLAB program to you. So for that, I'm going to have to move the MATLAB screen here. So I'll quickly go through what I already did because it's been a day now. But essentially, we clean up the MATLAB environment. I told you why we need to do that, or else the program before and the program that you're running now will all get mixed up in terms of the variables. And then we initialize ROS code. You have to get the IP address if you have a dynamic IP and start ROS code. So that's all standard stuff. And then I mentioned how you do the publishing and subscription, the publisher and subscriber setup. So this is for giving commands, so that's a publisher, and this is for giving the odometry, and so that's a subscriber. And I also have something called model state, which I explained yesterday, which gives you the true state of the robot is only possible in a simulation world, not in the real world. So we call this ground truth in robotics. So ground truth means the absolute truth, the God's word, Now similarly there's ground truth in a real world application, but the ground truth is an approximate ground truth. So you may have a way of measuring location which is much more accurate than others. So for all practical purposes, you can consider that to be, the word of God. So you call that ground truth. In the real world, there is no such thing as absolute truth. Nobody knows the exact location of the robot. Nobody. It's not possible to find out. And most things in life are like that. We often manage with less than 100% accuracy, right? When we drive a car down a main line, we are not precisely in the middle of the road, and it doesn't matter so long as we are not too far to one side or the other. So many of life's activities can be conducted without absolute knowledge. Okay. So then I get an instance of the object, and this is what I'm going to load up with in terms of the velocity values. So velocity is 0.4, rotation rate is 0.2, divide one by the other, you get a radius of 2 meters. I then calculate the circumference because I'm going to use distance of travel to stop the robot after it does one full circle. And then I calculate the time to cover that distance. So I'm actually using time of travel for a full circumference, not distance, but time of travel, which is calculated from the distance. So now I'm putting in velocities. So 0.4 and 0.2 that goes into the object, which is set aside for commands. Now this is the other part, getting data in from the odometry. So receive sub-odom. You don't have to worry about model state. If you want to, you can try it and compare it with the odom results. And then I told you, I prefer not using these non-variable names, so I unpack it and put it into odom pose 1 and odom pose 2. You can call it X and Y if you like, but odom pose 1, odom pose 2 is the same array. Okay, now, yesterday I said, you're wondering how I figured out that odom.pose.position X is the right value. So I ran the program. If you run the program, you won't get the variables here. You have to run the MATLAB at least once. So once you do that, you can figure it out by double-clicking on odom. So ROS has a complex message structure. There is a header, and there is the time that the data was taken, and so many other things that we don't need to be bothered about. What we are most interested in is the pose. See, the twist is there. The twist is the second part, which we saw on the Ubuntu side. But right now we're concerned about pose. So don't worry about the covariance. Pose, and there's the position, and there's the orientation. So if you click on position, you will see X, Y, Z. And if I click on, for instance, if I click on X, that's the variable for X. So similarly, if you want the angle, you can go back here and say orientation. Remember the quaternions? It's 4 numbers. I haven't told you yet how to decode it, but those are the 4 numbers of the quaternion. And this XYZ is not the same as unrelated to the other XYZ. So the initial ODA values, X and Y, I unpack, and then I initialize my plot variable. So I'm going to keep on adding to this. It's going to become an array shortly. The next point will make it an array and then it will keep on growing. This is not the best way. MATLAB doesn't like it because it slows down the computer. But visually or to understand the program, this is a better way of doing it. And then I introduced you to this technique of running the loop at a fixed rate, not running it as fast as your computer can run it. Because in real-time applications, it's never a good idea to run a loop as fast as you can run it. Because if you run it as fast as is needed, the rest of the time is available for you to do other parts of the MATLAB program. Here we're not doing anything else, but it's just a good practice to run the loop at the rate needed. Now for these kind of robots, whose maximum speed is like 2.2 meters per second, even 10 milliseconds is too much. For self-driving cars, which are, they can go at speeds of like 70, 80 miles per hour in the US, 100 milliseconds is the sampling rate. They will not sample any faster than that because you are making your processors work much harder than is needed. So I initialize the robot travel time. I reset the clock, because I have to, right? Because when you're timing something, you have to start with a reset. It's like timing a runner in a race. And then I'm checking whether the robot travel time has exceeded the time to go around the circle. Now initially, obviously, it won't have because you initialized it at 0. And then the first thing you do in the loop is you update it. If you don't update this, it'll run forever. Got it? Obviously, the loop will never be completed unless you keep pushing RTT to the new value. And so the rate object, this part of it, gives you the elapsed time. That's why you need the reset. Elapsed from when you reset it. That's what it means. And then I told you have to keep on telling, even if the velocity has not changed, typically you have to tell the robot drive, 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 because it's supposed to be a safety feature that if it stops receiving those commands, it will stop. That has not been programmed at all in Turtlebot 3, but you'll find it on many other commercial robots. Then you publish it, because you've already packed the velocities up here somewhere, and so you can publish it. In your task, if you want to change the velocity, you change the velocity and then publish it, right? So the logic is now emerging. Because if you want to drive the robot like this, then you have to change the velocity. So now you have to get a fresh odometry reading to put it in the plot variable. Because you want to plot the circle. So I receive and do the same thing again. And I add, I augment X and Y. And then I burn the rest of the loop time. So if you had other tasks to do, then this time will be handed over to other parts of the MATLAB program. But here it's just going to wait till 100 milliseconds are up. Earlier I think I misspoke. I meant that robots at the speed, you use 10 Hz sampling rate. So 100 milliseconds interval. For self-driving cars, you use 100 Hz sampling rate. So 10 millisecond intervals, much faster. And that's it. It'll come out of the loop, hopefully. This is a program that ends. Typically robots go on forever, right? And you hit a Control-C when the mission is done. Here it'll come out. And then you can stop the robot with this command. So when you trace out that L in the homework, you need to stop the robot, or else the plot will go like that. So you need to stop it when the L is done, the L shape. And then this is the standard way to plot things. MATLAB's plot routines are very powerful. You can make it very fancy, suitable for publishing a book, textbook, or paper, or whatever. So you can do whatever you want with it. You can add to it if you want. And then I do a raw shutdown. Now, typically, because you interrupt a program with Control-C, it will never come to this part of the program. It will always be in that loop. That's why I also put it up there. In case you have a program that does not finish, then this raw shutdown will catch it. So let me just show you that it sort of works. You see here, this is the imperfection of the real world. It doesn't quite make it because because maybe you should make your sampling interval a little smaller, and then you will you can't bring it precisely around the full circle, but maybe you can complete a little bit more, or maybe overshoot just a little bit. But here it's undershooting, it's stopped. So any questions? So let's take a quick look at the homework. So I finished the draft. So I'll finish this evening after the class. I'll create the final version, and then you can get started on it. And I told you, post questions on Teams if you're stuck. So the yellow highlighting is for me to resolve. That's why it's highlighted. So this is what you're doing. Thickness is not important. So you're going to drive this and stop it here. So basically you're going to model this with multiple sections of a circle. Maybe this is one circle, I don't think so. But maybe it's two circles, right? So you'll find out when you do it, don't spend like 10,000 hours on it. If it looks like an L, it's okay. But maybe you want two circles here, another circle here, another circle here, and then two circles here, and maybe one or two circles here. So when you start doing it, you realize, how many you need. So that's basically it. I also want you to fill out this table. I'm allowed for 10 segments, but you can extend the table if you want. Fill in. So you're going to make a choice, right, of V and omega for each segment. So just fill in the V and omega and the calculated radius. So there's not much to do in this homework. Now, I believe I asked you this before, but I want to make sure that everybody got it. So if you want to go this way, right, then V and omega are positive. If you want to go this way, V is positive, omega is negative. So you might not always be able to go, at some point you're going to have to change. So omega has to become negative then. So omega negative will give you a radius negative, right? And because positive by negative is negative, V by omega. And you're used to thinking that how can radius be negative? Now you are correct in a general sense, but in robotics, the radii can be negative. It means that you're going counterclockwise around a circle. I'm sorry, clockwise around a circle, R is negative. If you're going counterclockwise, R is positive. That is the robotics convention. So you can have R negative. Any questions? Okay, so I'm going to shut this down. I'll finish this up tonight and post it. So this is a PowerPoint that I posted maybe yesterday. I'll quit this. Do you have it? It's in the Teams folder. And kinematics and control. Okay, we go into the projection mode. So this is this is not deliberately made it simpler, because we just want the concepts of what a kinematic model is versus the dynamics model. And this will be true even in medical robotics. You'll have to deal with the kinematics of motion as well as the dynamics of motion. So you have different cars, right? They don't make just one car for us to buy. They used to do that in the old, Soviet Union. The communist countries used to make just like 2 or 3 cars. So we have so many more models now. So robots are similar, except that all cars are alike in terms of how they drive. They have a driving mechanism known as Ackermann steering. And maybe tomorrow you'll see a picture of what Ackermann steering is. Ackermann was the name of a person who probably had the first patent for it. But this is not Ackermann steering. This is a differentially steered robot. So it has 2 drive wheels. So I took 2 images for it because you can't see all 3 wheels in one image. So here's one and here's the other. These are the 2 drive wheels. So this robot rolls. Of course, if you hit it from the side, it's going to skid. I'm not talking about that. In normal driving, it rolls. Both drive tires roll, and the third wheel, which is a caster wheel, you don't have any caster chairs here, but normally it's the chairs with that flip-flopping wheel. So that wheel will do whatever the drive wheels ask you to do. It will come along. It's a passive wheel. So essentially, if you want to go straight, both of these wheels need to be driven at the same velocity. So in the case of the turtlebot, we used 0.4 meters per second, remember? Okay, now, that's the forward velocity of the robot, but that's not the velocity of the wheels. The velocity of the wheels, you'll see tomorrow, contribute to the velocity of the chassis. The velocity of the wheels can be different. If they are the same, the robot will have will move on a straight line. But if the right wheel is faster than the left wheel, it's going to turn around this way, right? And similarly, if the left wheel is faster than the right wheel, it's going to turn this way. Also backwards. You can go backwards and turn this way, or you can go backwards and turn this way. We'll see all that as the next 2 lectures develop. But this is a robot that has no conventional steering. It's not like a car or like a bicycle where you turn the wheel. This turns because one wheel is going faster than the other. So it's known as differential steering. It's a robot that is very popular till you get to about 125 kilograms. After that, they switch to what is known as skid steering. We'll see that also tomorrow. Skid steering is slightly different. This vehicle doesn't skid in normal operation. Okay, now, so my point is this, that an Ackermann steered vehicle, a skid steered vehicle, a differentially steered vehicle, they will all have different ways of moving. And before you can control them, you have to know what the capability is in terms of moving. Okay? Because you're not going to design a control system unless you know how the vehicle moves. So dogs are on 4 feet, humans on 2 feet, It's not the same. The motion is not the same. So that's the reason for studying the architecture of motion. Now, why do we need a model at all? Now, it's never the practice anymore. Maybe it was in the 50s and 60s to do any engineering design without going through a simulator. Because it saves you a lot of time and effort if you run ideas in a simulator, eliminate ideas that are bad, and then you finally have like 2 or 3 ideas you want to test out in a real life situation. So basically, that's why you have motion models, software models for the robot. So that's what we're going to talk about here, primarily the kinematic model, but I'm also going to tell you why dynamics is important. So dynamics is very important. It becomes less important in certain situations. It's never unimportant. If it's important and nobody pays attention to it, you know what the reason is? Convenience. So because of convenience, they say ignore it. But eventually it's there, you can't ignore it, right? In some situations, you can get away with a kinematic model. And those are when you're moving very slowly, or you have such powerful motors that the dynamic effect is not going to be really showing up. So if you have very powerful motors, then maybe you can ignore the dynamics. Or the vehicle is so light that it turns quickly. Otherwise, you cannot avoid dynamics. It's a fact of the real world. All cars don't behave the same when you turn, right? If you have a big truck and you want to turn it into a narrow lane, it's different. At high speed, definitely different. Okay. Now we're not going to do control theory. That's a separate course, or 2 or 3 or 4 or 5 classes, depending upon how deep you want to go into control theory. We're not studying control theory. We will see it in the form of an exercise, the next homework exercise. You'll be able to see controls by writing software for the things. So this is the formal definition from Wikipedia. Kinematics is a branch of classical mechanics that describes the motion of points, bodies, and systems of bodies without considering, see, this is the key, without considering the forces that cause the motion. So when you are studying kinematics, forces never enter into the picture. Masses don't enter into the picture. You don't really care. You are moving from the velocity onwards. So maybe I should quickly flip to this. This document. I avoided writing on the board by creating. I created the same equations here. So you remember this equation from physics that if your initial velocity is vi and your final velocity is vf, then the way to get from initial velocity to final velocity is through an acceleration, right? You remember that? Now in kinematic studies, we don't care of the time difference between vi and vf, the fact that we can't change vi to vf instantaneously. We move from velocities onwards because if you want to do that, you have to study, Newton's law. So forces, masses don't enter into the picture for kinematics. We'll get to this again shortly. Okay. Dynamics, on the other hand, is a branch of physics concerned with the study of forces and torques and their effect on motion. So you can say that dynamics starts more upstream. Velocity is downstream. And in kinematics, they jump on the thing downstream. They don't worry about how force converts to velocities. They just assume that velocities are given to you. They work from there onwards. You can read this bullet yourself, but maybe I jumped too quickly away from the other document. So this is the essence of dynamics. So you want to change your current velocity to a new velocity, right? And if you have a constant acceleration, then you let certain time elapse, and then vi becomes vf. So therefore there's a delay, right? You can never go from one velocity to the other instantaneously. If you're a runner, right, and you see the finish line and you want to accelerate, you can't change your velocity instantaneously. There is a delay. Some athletes, there's a smaller delay. Everybody has a delay. But the better athletes have a smaller delay, right? There's no such thing as zero delay. So that's a very important aspect. So if you have a Formula 1 race, obviously dynamics plays a role. However, let's just argue this out theoretically. What would it take for velocities to change instantaneously? It would require an infinite acceleration, right? So that's what kinematic models assume. They assume the acceleration is infinite. Or remember, in practice, they say it's so large that we don't have to worry about the dynamics effects. So that's the approximation people often make in the real world. There's almost no dynamics. If your acceleration is so high, ideally it should be infinity. There's no such thing as infinite acceleration. So they assume it's very high for this particular situation. So I don't really care about dynamics. But what does it take to have infinite acceleration. Newton's law says that either the force must be infinity, so it's like saying I have infinite forces, very powerful motors, or your mass has to be extremely small, right? Or it could be both. It could be a huge force and a very small mass, a combination of the two. So that's the thing. When they ignore dynamics, they're basically saying, I have a situation where the mass is almost nothing, or the force is infinity, or a combination of the two, or I don't care. I want simplification. I don't care what the actual situation is. I want to start with a simplified model. So that's when the kinematics model is valid, because dynamics models are complicated. Okay, now going back to the PowerPoint. So you have to at least know the kinematic capabilities to do simulations. And that's what we're going to do, because we can't study dynamics in this class, there's not enough time. A couple of my students are working on modeling the dynamics, two of them on different ways of modeling the dynamics. Ultimately, you have to do it. So another way of understanding kinematic capabilities is, you're in a car which has stalled, right? And you're trying to get your friends to push it into your driveway. So now you don't want to go too fast, because you know when a car is moving slowly, it's hard to turn the steering wheel quickly because there's friction. So you want them to push, and sometimes if you can't turn in, you stop the car and turn the steering wheel. It's not good because the tires are rubbing against the ground. But what else can you do if you want to get into a narrow driveway? So kinematics is slow rolling motion. So in other words, the mechanics of the motion, right, is purely based on time being available for any amount that you want, you have the time. So it's slow rolling motion. It's basically the footprint of the robot. What is the possible footprint or envelope of the robot in slow operation? And this is a good example because I don't know whether you know what a limo is. Limo, the Hollywood stars show up in it. A limo doesn't work the same as a Beetle in terms of how it handles. So even cars, these are both cars, same Ackerman steering, but a limo does not feel the same as a Beetle. So, but at least you have to have the kinematic capabilities represented. Then if you have the resources, you can do the dynamics also. Once you have that model, then you can investigate how to control the motion capabilities. So the control is not universal. The control is for a particular vehicle's capabilities. At least kinematic, but if you can manage it, also throw in the dynamics. So obviously in a Formula One race, they have to worry about the dynamics. How quickly it changes lanes and so on and goes around corners. That's the whole battle there in Formula One. They're trying to optimize the vehicle to be able to turn without skidding out. Oh, I didn't expect that. So we can't even see this. So we have lost the resolution here. Yeah. I'm wondering how else I can make this figure. Did it show up in Word better or? There's supposed to be a figure of 8 here. But we can come back to this after I do the model. So let me continue for now. Yeah, we'll just leave it. Just a quick comparison between the kinematic problem for manipulators. The manipulators are those robots with arms, as used in medical robotics. And the other half of robotics, their cousins, mobile robots. They are on wheels. I told you that localization is much easier for manipulators, not that easy for mobile robots. So here are the questions you ask, and you see there is similarity. even though they're two separate fields, there is similarity in the problems associated with each area. Localization is a problem for both. Maybe easier in one, but it's still the same problem. So these are the questions you ask. Is the manipulator arm capable of reaching a certain point with a desired orientation of end effector? So imagine if I have a workspace like this, and I need to pick up something here, right? So I need to know whether, with all the joints, how many joints do I need? Are the angles sufficient to pick up this? That's the challenge you face in factory automation. Now, factory automation, you have an advantage. You're going to prevent people from walking around, looking for a cup of coffee. Because you have the ability to completely organize your environment. With mobile robots, you don't have that luxury. You have to, self-driving cars, you have to deal with whoever is there. Even a pedestrian who's not supposed to cross, if he or she crosses, you have to deal with that. But the factory automation space is, you can control it much better. Mobile robots, on the other hand, they have to deal with the real world. People walking across, right? And suddenly you encounter a bad road, then you still have to be able to drive on it, right? Odometry is horrible in bad roads. You know why? Because if you have potholes, then the wheel rotations don't mean the same thing as on level ground. Because sometimes when you hit a bump, the tire will come off the road, it will spin, odometry will be recorded, but it's really not making ground, right? So it doesn't mean anything when the wheel spins in the air. So you have to deal with all those problems. That's why odometry cannot be relied on for long. You need some kind of correction. So here are the challenges for the mobile robot. How maneuverable is it? Is it capable of operating in an extremely cluttered environment? And this is the next example. Consider that you have a disaster scene, an earthquake, and you're sending in robots to rescue people who are still alive, injured people. So you can imagine, is it capable? So they have snake robots now, because I've seen, in an earthquake scene when the whole building has collapsed, regular robots with wheels are not going to accomplish much. So they have these snake robots that can go through the holes and look for the warmth of humans, and then will conclude that there is somebody alive, and maybe deliver some water to keep them alive till rescuers can get to them. So the snake robot has a particular mobility that suits that application. The regular car is not going to help you in that situation. Maybe the car will get you to that point, but then something else has to, take over. So here's another example. Can it operate in tight spaces? So let's say that you're going through a minefield, a military vehicle, just demining. Your localization has to be precise. You can't be off by a foot or so here. So if you have a map of the minefield, then you want to be very careful where it drives. So you can see the problem is much more difficult here. But manipulators also have a problem, because I told you there's something like 22 degrees of freedom in an arm. So now you have to control these 22 degrees of freedom in an intelligent way. Now, of course, human beings do it naturally because we learn as we grow up. But if you have like 22 degrees of freedom, you've got to figure out, do I do this first and then this, or the other way around, right? So there is that sense of optimality. What is the quickest way of picking up that object? In ports and docks and all that, time is money. So you want to unload as quickly as possible. So you don't want to take something like this and then put it here. I'm just joking, but you know the point, right? There is an optimal path, so you have to figure out how will you change these angles to quickly take this object and put it there. Unload, basically, quickly, so that they don't charge you. So, this is the robot we have back at my university. It's called Clausen. I think it's quite expensive. I'm guessing at least $2,000. It's ROS capable. So imagine taking one of those and putting it here. Now both the problems of both worlds are now joined, because localization is going to be difficult now because the base is no longer fixed. It's sitting on this robot, right? So this would be if you have to go by some injured person and administer some aid. So now you've joined the two worlds of robotics together. So as I said, it's easier to organize the factory floor so that you don't clutter it with toolboxes or human beings or whatever, dogs. You can completely clear it. Now this is just to make you aware of the two environments we live in. So one environment is known as structured. So this is a structured environment, you know. So even a dorm room of a student, no matter how badly it is kept, is a structured environment. It's more, okay, let me put it this way. It's more or less a structured environment. It can be made more structured if you fold your clothes and not just throw it around. Okay? The forest is an unstructured environment. So mobile robots have to deal in unstructured environments, whereas the other robots, other types of robots typically deal in structured environments. But of course, if you take this and mount it on that, then that is no longer valid. Okay, now forward kinematics. So this is the easier problem to solve compared to inverse kinematics. And you will understand why as soon as we go through this. So forward kinematics is the process of calculating the position in space of the end of a leg structure. So in my case, it might be the tip of my forefinger. So end of a leg structure given the angles of all the joints. Now that has only one solution. If you tell me what this angle is and this angle is and the length of this, pretty much, it's possible to calculate, where the tip of my finger is, right? So one solution, easy. There are a lot of matrix operations, but it's easy. Basically, the theory is easy. Inverse kinematics is the opposite. I want it to be here, and initially I'm here. Now you tell me what is the best way, quickest way of getting here. There are many solutions, right? So when you have a factory robot, and you're telling it, go and spot weld that place on the car, then, you can't be, doing this, and so you have to hurry up because the thing is moving. The assembly line is moving and you want to push more cars through, the assembly line. So there's many solutions, right? So you have to find the best solution. And if you put obstacles in the environment, it becomes more difficult to solve. So the inverse kinematics problem is much more difficult to solve. Now we talk about the same things for mobile robots. So forward kinematics for a mobile robot would be, and here I keep telling you the V and omega that I used at different intervals of time. So T1, V1 omega 1. T2, I give them the whole thing. So for the differentially steered robot, imagine little tiny circles, right? So the V1 omega 1 for a certain time will produce a circle, right? And between velocities, we assume that, it's the same velocity. And that it changes in, see, dynamics. We should really be using dynamics, but we're going to assume that V1 and omega 1 is held steady till the next time. And then it becomes V2 omega 2 immediately. It doesn't in practice. But let's assume that we can assume that. So it's possible to figure out little tiny circles, we can figure out where we are, right? One solution again for a mobile robot. The inverse kinematic problem will be, I want this robot to go to the second row from the end and find a bomb there and align itself in a certain way because it must be facing the wires to unplug. So it must really get there oriented. It can't be on the other side of the bomb. It has to be in the front side of the bomb and oriented properly. So many solutions again, right? So how should I drive it so that it goes as quickly as possible into that second row and orients itself with respect to the bomb? So again, many solutions. Now, you can ignore dynamics if you say, take it easy, go very slowly, but sometimes, when there's a bomb, you have to go quickly. So you might not have that luxury. Or if somebody is lying injured, a baby is lying injured, you have to go and pick it up gently because there might be broken bones. You have to go quickly. You can't say, I don't want dynamics to play a role, so I'm going to go slowly. Right? You have to go fast. It depends on the situation. Alright, so now we're going to go to another slide set, which I think I posted it in the Teams. Let's go. Should we take a break at some point? No? Okay, what time is it now? Okay. No. So I'm going to pull up, okay, I can show you this. That's the one. So I'm not going to go through every single slide of this. This is just to establish the kinematic model of the turtlebot 3, which is a differentially steered vehicle. So this is not mine, it's from Professor Chris Clark. He moves from university to university, but these are his notes. There's a lot of interesting stuff, but not relevant in the short time we have. See, here they're trying to create a model of a person walking. So why would they do that? It's because they're doing gait studies. You can work with a real human being in the real world, but that's going to be a problem. Like, how many experiments can you conduct with a real human being in real time? So if you have a model, you can try out all kinds of ideas. You see this robot here? This is meant for clearing trees. It's pretty scary. You can, on YouTube, you'll find videos of this. Somewhere here there was a snake robot. I wanted to just show it to you in passing. Or maybe I'm thinking of some other presentation. Drones. There it is. So it is a snake robot, and it moves just like a snake. It slithers side to side like this and creates forward motion by compression, basically. So slide 21, I think, is where you begin. So this is the most important aspect of robotics from this point of view. If you want different robots to talk to each other, jointly create maps and so on, there has to be an understanding of what is your axis of reference. I think I already gave you a sense of that, right? If one robot is facing this way and sees something, another robot is looking at it from here, and you're trying to create a map, you have to compensate for the different viewpoint. Otherwise, your map will be all over the place. So, we're going to talk about global coordinate frames and local coordinate frames. And then the need for transformations. So, ROS does it automatically, but we just want to understand why it's doing that. And then forward kinematics, specifically the differentially steered vehicle. What are the equations that represent the kinematic model? Now, when you're trying to come up with a model, you have to have an idea of what are the most important variables you're interested in. So you put everything into that and you call it the state vector, right? Now the color of the robot might be interesting to you, but it may not be relevant to engineering design, so that doesn't belong there, right? So for instance, if you say what is the state of a person, you might say how tired that person is, how much money he has in his wallet, etc. That's the same thing here. What are the most interesting things about a robot? Then we have differential equations that apply to the state variables. In some way, the laws of physics applies. So only then we can control it. Once you have a model, we can control it. We need the state variables and we need the differential equations for it. So I talked to you about this briefly. The global frame, right, is that one frame. It's imagine like a axis, 3-axis system buried at 0, 0. You saw that. That's where the robot started. Robot doesn't have to start there. It has its own frame. But here, when it starts, both the robot frame and the world frame are coincident. But the robot will move away. Right? It will take its frame with it. Obviously, it has to. So you know of at least 2 frames. But then if there's a camera on the wall, camera on the wall or a camera on a tree outside, and it sees a student bunking class to go to a movie, then that camera is looking at the student from its own perspective. So it has its own frame, right? And there could be 50 cameras around campus. So 50 frames. There could be 50 robots with 2 or 3 cameras each. So can you imagine? The number of frames multiplies. No human being could sit down and do the calculation. This has to be automated. And this is done in robotics in ROS by a thing called TF, transforms. So it is a package that's built in and you just use it. You don't have to set it up or anything, it's available there. So that's why you need frames. Because if you want to build a map and robots are looking at the same thing from different angles, you have to somehow reconcile the different views. Now the global frame is also another name for the world frame. So these are all the same names. Global, inertial, world frame, all the same. The local frame, I've given you examples of robot frame or camera frame or robot tools frame, you know. There can be many local frames. There can only be one world frame. But there can be many fixed frames. That's not the same thing. The world frame is a fixed frame. You can have other fixed frames, but there can be only one world frame. That means if you imagine a tree structure, the world frame is at the top. How do other frames join their data through the world frame? You got it? The world frame you can count on, it's not moving. All other frames, they can only understand each other through the world frame. Somehow you have to refer it to the world frame, then everybody understands it. So even if robot 2 wants to know what robot 1 saw, robot 1 has to first transform it to the world frame. Then the world frame you transform it to the second robot. Not direct, because the organized way to do it is everybody goes to the world frame and then comes down. Alright, we look at that. This is a kind of a live PowerPoint. Things will pop up. So here, this is what we want to see. Now I never formally defined theta. Remember xy theta? Now I'm going to do it. So theta is the heading angle. So this is in 2 dimensions, not a drone. So this is theta. By definition, the angle is with respect to the positive x world axis, not the y-axis. Remember, theta is the angle made by this line drawn straight out of the nose of the robot with respect to the world. See, I is inertial, is the same as world. So that's theta. It's called the heading angle. I also told you one of the problems with angles. 360 degrees is the entire range, right? In fact, in robotics, they don't say 0 to 360. They say 0 to pi, and then 0 to minus pi. So in other words, minus pi to pi. They don't use 0 to 360. Or the equivalent of that would be 0 to 2 pi. They don't use that. By agreement, it is minus pi to plus pi. So this creates a problem when you're writing code, if you work with angles and degrees, or even in radians. At that point, at this point, right, you may have an angle of minus 179, right? But if you move a little bit there, it becomes, let's say, 181, plus 181. That's not a big change in angle, but if you work with this system, you will think that something huge has happened here. So sometimes you find the robot spinning around because you've given it the larger of the 2 angles. And it will spin around and then point again in the same direction, or almost the same direction. So that's why we use quaternions. If you work with quaternions, you'll never have that problem. So this is called a wrap, W-R-A-P issue, angle wrapping issue. It's an issue with angle wrapping because we are supposed to wrap it. Some people say unwrap, but you know what we're talking about. Some people say it's an unwrapping issue, some people say it's a wrapping issue. But the point is, you can't allow the angle to exceed pi. And you can't allow it to go below minus pi. Okay, so that's the heading angle. And this is the state vector for the robot. See, x, y, and theta. And that is the state of the robot. with respect to the world axis. If you're curious, this is a Greek letter which is pronounced psi. That's how it's pronounced. Typically, you write these as column vectors. That's why they transpose. They write it horizontally to save notebook space, and they put a transpose. We'll do this one slowly. So this is the robot's frame. You understand now? The robot's frame is red axis. Remember the red axis? So red here, green and blue. We don't care about the blue because we are moving on a plane. But XR and YR. So the robot is going to carry this axis with it. Because if it left it behind, it will be useless to the robot, right? You always want to know what the robot sees, you don't want to leave the axis behind. So, what is the state of the robot on its own axis? Well, it's carrying its axis, right? So it's always got to be 0, 0, 0. Is that clear? The robot is carrying its frame. It better not be anything other than 0, 0, 0. It just can't. So you're wondering, what is the use of the robot's axis if it's always going to be 0, 0, 0? Well, the robot doesn't want to measure itself from itself. The robot wants to measure some other object. So the robot sees an object, right? The robot is not going to use the world axis. That is not natural for the robot. It doesn't even know, okay, where is the world axis? It's far behind there. So the robot sees objects, people, bombs, with respect to its own axis. So here is the object. And the other thing, before we take a break, I just want to mention that the most natural way that you see things is not by x and y. It's by polar coordinates. So polar coordinates or range, the distance, always positive. Range cannot be negative. So range and bearing. So just like we had heading angle, this is known as the bearing angle. B-E-A-R-I-N-G. So, is there a sign convention? Yes, there is. Because this right now is negative. This is negative, this is positive. So anything, remember, counterclockwise is positive, right? The same thing here. Counterclockwise is positive, right now you're seeing a negative angle. So rho and alpha. So let's take a break of 5 minutes and then we'll continue. Okay. So as I said, the natural way for a robot to look at its surroundings, even for us, is by range and bearing, not by world coordinates or x and y coordinates and so on. However, before you transfer it to the world frame, remember I was talking about transforms, you have to convert it to x and y as the first step. So here it is. The first step is just the first step. There will be many such trigonometric operations, but you project the range and bearing of the object to the local robot axis. And you will remember these equations that you take rho and you project it here and project it here. Now one thing that you'll be tempted to do is try to guess whether x should be negative or positive. Shouldn't do that because the sign of this angle automatically takes care of that. So right now alpha is negative, right? Remember I told you it's positive on the other side of XR, it's negative on this side. So alpha is negative right now. So when you put a negative angle in here, then it will automatically sort itself out because you get cosine of a negative angle and sine of a negative angle. So the y will be negative, as it should be, because look at the projection of this, it's somewhere here. So the y projection should be negative, and that's what will happen if you put in a negative angle here. Do you get that? If you put a negative angle here, y object will be negative, and you can see the projection of this on the y-axis should be negative. See, this is positive y, this way. Is that clear? And the x-axis, the angle should not matter. So when you put in a negative angle, you still get a positive number. So that's the beauty of trigonometry. You should try to do its work for it. It will automatically do the correct thing. Alright, so that was the state as far as position is concerned. But now you also have the velocity states, right? You're also interested in how the x dot is changing, y dot is changing, and the theta dot is changing. So these are the three velocities with respect to the robot axis. So this is forward motion of the robot, this is sideways motion of the robot, and for a differentially steered robot cannot happen, 0. But now we're having a general discussion, so we can't make it 0 now. For a differentially steered robot, yeah, it will be 0. Theta dot is the rotational rate. And this we call psi dot r with respect to the robot. Psi dot r, earlier we had psi I, remember? Right here, no. Right here, psi I. So that's with respect to the world frame. And now this is with respect to the robot frame. Now, you will realize that x dot is our old v symbol. X dot, forward velocity of the robot, was what we called v. It's not something different. X dot is the same as v. Y dot is equal to 0. So I put for a differentially steered robot only, 0. And theta dot is 0 omega, radians per second. We start by transforming velocities. Position, I'll tell you what it is, but we don't want to get into the details of that. It's not relevant for this course. But we'll first transform velocities. So, if you're driving a car, right, and you know the velocities with respect to yourself, but somebody might be interested in putting your car on the map. So for that, you have to transform these velocities. Your velocity is the local velocity on the road. Your velocity will be the same even if you take a turn in the road, right? But on the global frame, somebody wants to plot where you are. So for that, you need to convert these velocities first to velocities on the global frame. So that is typically done by a transformation matrix. R of theta takes velocities in the world frame and converts it to velocities on the robot frame. On the other hand, R inverse does exactly the opposite. R inverse is the inverse of this matrix. I'll tell you what the matrix is shortly. So R inverse is just the inverse of this matrix. Depends on which direction you want to go. If you want to go from the world to the robot axis, it's R theta. If you want to go the other way, it's R inverse theta. Why is one inverse theta, the other R? It's because somebody in robotics decided that this is the way it's going to be. R is assigned to going from world frame to local frame, and R inverse is the other way around. One is the inverse of the other. So here, simple equations. So this is your XR dot, otherwise known as V. So XI dot, see here, XI dot will be how you progress along the world's x-axis is XR dot cosine theta. Is that clear? And similarly, yi dot is xr dot sine theta. Xr dot, if you take it the other way, you get yi dot. How you are progressing here. So, without going through the details will always, I always tell students that you have to understand the concept first. The math will sort itself out. If I know xi dot and if I know yi dot, how do I track the progress of this robot on the global frame? You should be able to integrate this theoretically. If you integrate xi dot, you get xi as a function of time. And if you integrate yi dot, you get yi as a function of time. So if you keep on doing that, you'll be able to figure out where the robot is on a world frame. And so you can track all robots. If you track them locally, it's not going to be interesting to the person in the control room. They want to know, if they have a flag for each robot, they want to know how these flags are moving on the global frame, right? They don't care much about what the robot is doing locally. This is the only way to do it. You have to project to the world frame, which is a common frame. And then integrate it. What about rotational velocity? What is the transformation? It's the same. If you have a rotation rate with respect to the robot, it's going to be the same as the rotation rate with respect to the world. Do you agree? Just imagine it. You're rotating at a certain rate. Why is it going to be different if it's a robot or a robot frame or the world frame? It's going to be the same. Not the x and y. The x and y have these equations. But the rotation rate is identical. So theta I dot is the same as theta r dot, and that's what we call omega. You have to remind yourself, theta r dot is nothing but omega. X r dot is nothing but v. Y r dot is 0 because a differentially steered robot is not capable of moving sideways unless somebody hits it from the side. We are talking about normal motion. Okay, so we take those equations and try to put it in matrix form. See, it's the same thing. Xi dot is equal to cosine theta times xr dot. Yi dot is sine theta times yr dot. Correct? Theta I dot is 0 times xr dot plus 0 times yr dot plus theta r dot. So theta I dot is the same as theta r dot. So, we use matrices for compactors, right? So that's why, otherwise we'll be writing, 5 equations when we can just put it in a compact matrix. Why is it coming here? Because something extra must have happened. Here it is, yeah. He's labeling this. This is your psi r dot, the state of the robot's velocity. And here's the state on the world frame. And this is the transformation matrix, which is called r theta inverse. Now what happened here? This is for a special case. Of a differentially steered robot, yr dot is always going to be 0. So what's the point of using it if you know that anything multiplying it? So what multiplies yr dot? This entire column, right? So if you get rid of this, you also have to get rid of this column. And that gives you the compact representation here. Check it out. If you get rid of this, you have to get rid of everything that multiplies it. And you get this. So this is only for a differentially steered robot. And now we are finally ready to come up with a forward kinematics model. Okay, now I want to repeat something I said a few minutes, not a few minutes, but at the beginning of this session. So the forward velocity, no motor is dictating the forward velocity. There is no motor that is directly generating forward velocity. It's these two wheels here. The two wheels are spinning, and as a result of that, you're getting forward motion, right? But if you're going to engineer the vehicle, you're going to have to go down to this level. So so this is not a minus sign, by the way, it's just dash. So phi 1 dot is the rotation of the right wheel. So a motor directly can control that. Phi 1 dot is the rotation rate, radians per second. So if you connect a motor there, it's going to spin it, right? So how fast, what is the fastest speed? You have to say, okay, what are the motor specifications? So it's directly related. Same thing with the left wheel. The motor is directly connected here. V does not have a motor driving it. Whatever happens to these two dictate what happens to V. Similarly, you're going to find out whatever happens to omega is because of the rate at which you're spinning this. If you spin both of them at the same time, omega is 0. Right? If you spin both of them backwards at the same speed, 0. You have to have a difference between the two rates in order to swing this way or swing this way. So we're trying to establish the math here. So phi 1 is right, 2 is left. That's because I've done it so many times. Later on, we're going to change the subscript to R for 1 and L for left. R right for 1 and L left for 2 to make it clearer. There it is. It doesn't show the third wheel, but it's somewhere there hidden. Or maybe it is supposed to be here. Basically, it's removed the third wheel. You need it because otherwise there won't be support. But it's unimportant, right? I told you the third wheel just comes with the whole body. So this is V of t and that is omega of t. This is the positive direction. And this is spinning at phi 1 dot and that is spinning at phi 2 dot. 1 is right and 2 is left. This P, this point P is not on the ground. It's actually up here between the two wheels. So if there is an axle connecting them, it's exactly the midpoint of the axle. So this is the center of, this is called the center of rotation for a reason. You'll see why. And this dimension, 2L, the technical term for that is the track of the vehicle. So 2L is the track of the vehicle. Deliberately, some books call the whole thing L, some books call it 2L. So if you read something in a book, you have to check what is the rotation it's using. Alright, now we're going to jump to the PDF document. Let me ask you a question before I do that. This is rotating at 5 on dot, right? In 1 second, how much of the wheel will roll out? Just think about it for a few seconds. This is going back to, I don't know, high school math or maybe an early math course. The radius of this wheel is r. Similarly, the radius of that wheel is also r. If this is rotating at 5 on dot radius per second, in 1 second, how much wheel will roll out? You remember that old rule? R times 5 on dot, that amount of wheel will roll out in 1 second, right? So let's assume the other wheel is also doing the same thing. Let me ask you this question. How far forward will the center of the wheel go over the same time? 1 second. It has to be the same R5 on dot. Because if the wheel rolls out to the extent of R5 on dot, by the way, if R is in meters and 5 on dot is the radians per second, R5 on dot will be in meters. So this has to go out forward by R5 on dot meters, right? How about the left wheel? R5 dot meters, right? So how about P, the midpoint between the two wheels? Now think about it. The right wheel, the center is moving forward by R5 on dot, the left wheel center is moving forward by R5 dot. What will be the velocity of the midpoint? It will be the average of the two. So immediately you can see that V is R5 on dot plus R5 dot by 2. So that's how you get V. It's the average of R5 on dot and R5 dot. And in fact, half the derivation is done. I wanted to do it by waving my arms around because we have this beautiful figure here. So now we go to the other document in the Teams folder, which is I think the math of kinematics or kinematic math or something like that. Let me pull it up. I have to find where it is. Oh, I don't have it here. I pulled it up from the Teams site. We close this. Here it is, kinematic derivation. So pull up the document with the title of kinematic derivation. It's not opening. Oh, there it is. So I can't draw in 3D, so this is my crude sketch. What I'm showing you is the right wheel rolling out by a certain amount. So I'm not using 1 second, and because to be rigorous you have to use dt. Dt from calculus, an incremental amount of time. The reason we have to do that is we have to allow for the fact that the velocity is changing. So calculus gives us this concept that we can assume that over dt, nothing is changing. In practice, I told you, we're going to assume that between two sampling instants, it's going on a tiny circle. That's okay, because if the samples are taken quite frequently, that assumption is valid. It's little tiny circles, right? Your L is not that tiny circles. You're going to do a little bit bigger because you don't have time to do tiny circles. You cannot be doing 100 circles for the L. So little tiny circle. So here dt. So the right field is V1 dt is ds1. That means this arc length is V1 dt. And V1 itself is R51 dot. So here it is. V1 is R51 dot. Is that clear? V2 is R52 dot. And if you want to convert it to a distance, then you take the velocity and multiply it by the incremental amount of time. So you get ds1 is equal to V1 dt is equal to R51 dot dt. And ds2 is V2 dt is R52 dot dt. What is the average motion of the middle, the midpoint M, which is also called P? That's why, here I labeled it as M, and so to avoid confusion, I said M is the same as P on the vehicle. So this is V dt, and it's the average of these two. So there it is. Pull the dt to one side, and that's the equation I was talking to you about. The velocity of the midpoint P is the average of the two V velocities. Now, the second part, to get omega, is going to be a little bit more difficult. So, that ds1 is equal to V1 dt is equal to R51 dot dt. I take this, this part of it. ds1 is equal to R51 dot dt. Okay, are you paying attention? This ds1 is equal to R51 dot dt. I take that and I extend it. Now, what is this R plus L? I got to see the diagram here. So, do you agree that if this vehicle is on a circle, there will be some center of rotation? Because remember the circle, the program I gave you? There is a center of rotation. If it's going this way, it's somewhere out there. That point has to be in the middle of the circle. Therefore, the radius of the circle is the distance between that and the midpoint of the vehicle. So this is R. The radius of curvature, that's the one we calculated as V by omega. So this is R, and here is L, half the track, here is the other half of the track. So if you want the distance between this and this, it's R plus L. If you want the distance between this and the left wheel, it's R minus L. And so, if I take R plus L, right, if I take R plus L, by the way, during this time, dt, I have moved v dt, right? At the same time, I am rotated by theta dot dt, right? And I'm rotating, remember the theta dot or omega, same thing, theta dot omega. So in that time, I have swung around a little bit, right? And this is how much I swung around by theta dot dt. So going back to the equations here, ds1, which is r51 dot dt from here, is also r plus L theta dot dt. Look at this. See, this angle is theta dot dt. So if I take r plus L and swing it around this way, I will get, the same thing as r51 dot dt, which is right here. Similarly, ds2, this r52 dot dt is r minus L theta dot dt. This time, instead of adding the two, I'm going to subtract number 8, equation number 8 from number 7. So R51 dot, no, the other way around, 8 from 7, yeah, right. So R51 dot dt minus R52 dot dt is, the R and R will cancel and giving you 2L theta dot dt. And then I solve for theta dot is equal to R51 dot minus R52 dot by 2L. dt dt cancels. And what is R51 dot? It is V1. What is R52 dot? It is V2. So this is the second equation. So this is the kinematic model. V equals V1 plus V2 by 2, and theta dot, which is the same as omega, is V1 minus V2 by 2L. So just to make sure you understand this, I'm going to ask you a few questions. Okay? Right wheel and left wheel are spinning at the same velocity. What is omega? 0, right? What is the average velocity? Either one, because it's the same velocity. V1 plus V2 by 2 will give you V, right? Right wheel is spinning faster than the left wheel. What is the sign of omega? Positive or negative? Somebody said positive? Positive. Positive is right. Left wheel is spinning faster than the right wheel. What is the sign of omega?
Negative.
Negative. I want to go backwards now. Right? What should V1 and V2 be? I want to go backwards straight. So both of them should be negative and equal value, equal magnitude and negative, right? I want to go backward and turn this way. So first question, I want to go backward and turn this way. Is omega positive or negative? First, that's the question. Focus on that question. I want to go backward and turn this way. So I'm going backwards around the circle counterclockwise. Positive, because think your axis is sticking out this way, it is still sweeping this way, right? It is sweeping counterclockwise, so positive. And of course, if I'm going backward in this way, omega will be negative. Because the axis is sweeping this way now, right? Okay, now. Left wheel, 5 meters per second. Right wheel, minus 5 meters per second. What am I doing? Huh? What is velocity? What is the average velocity? 0. But what is going on? What am I doing? Yeah, we're not stationary because we are spinning around a stationary point, right? Where is the center of rotation? So over here, the center of rotation is R this way or R this way. So when I'm just spinning, where is the center of rotation? Think about it. I'm not moving. Is the center of rotation directly below P? So V is 5 meters per second, V left, V right is minus 5 meters per second. I have no velocity because it averages out to 0, but I'm spinning, right, on the spot. So the center of rotation, center of curvature of the circle is right here, underneath. Does that make sense? It's right here. What is the radius of curvature? Go to the formula, V by omega. 0, right? It is 0. It is 0. So when you're spinning, the radius of curvature is 0. Now, is that good or bad for a vehicle's ability to maneuver? Can a car go this way? Suppose the car has to reach some spots here. It may not be able to go there. It might have to drive out and come back, right? But what about a differentially steered vehicle? I can just rotate its place like this, right? And I can get here. So it's much more maneuverable than a regular car, right? Because even the car, if you turn the steering wheel all the way to the stop, it might not be able to get here. It might have to drive out and come back. Whereas a differentially steered vehicle can pivot in place. So that is the beauty, because it has the possibility of 0 radius turns. Going back to an earlier question, when I'm going straight, left and right wheel, same speed, what is the radius of curvature? Just be bold and throw out an answer. You said 0 before. No? You're going straight now. So where is the center of curvature? Think about it. What is a straight line? Is a circle of radius with infinity, right? Infinity. Right. A straight line is also like an extreme circle. So the radius is infinity. Does that make sense? So where is the center of curvature? Far away at infinity. So everything fits in, right? Everything fits in. Now one more. The right wheel is stopped. V1 is 0. But V2 is some positive value. What is going on? It will turn. The right wheel is stopped, but the left wheel has a positive velocity. So you will circle around what point? You will circle clockwise, but what? Where is the center of rotation? Is it underneath the wheel? Underneath the right wheel? It'll be directly underneath the right wheel. Right? right? Directly underneath the right wheel. So what is the radius of curvature? So just imagine the circle. You're drawing a circle with the right wheel, not moving, because velocity is 0. But the left wheel has a positive velocity. So what is the radius of curvature? You can calculate it from p by omega, can't you? You should be able to do it from p by omega. The point is, we are rotating about the center, which is directly under the right wheel. So you can make a differentially steered robot do that too. If you stop the left wheel and you make the velocity of the right wheel negative, then it's going to rotate this way. But the anchor will be the stopped wheel will be the anchor. So that's how a differentially steered vehicle operates. I told you, till about 125 kilograms, they still use it. The only thing is this, you have to watch out. So let me try to draw something here. Not all differentially steered vehicles are circular. Because if you're circular, then your two drive wheels will be on the two sides of the circle. But where will you put your, that wheel that flips? It's called a caster wheel. Will you put it forward or will you put it back? Because if you put it back, then you can't load the front because you might tip over, right? So sometimes people use two caster wheels to provide, uniformity. But that will be a pretty odd vehicle, right? A circular vehicle going through the airport. So typically, those vehicles are made triangular. So it's like this with one caster wheel. You can put two caster wheels in the back also. If you but whatever the situation, if you have the drive wheels up front, you're wagging a big tail. Because remember, the pivot is what? P is right between the drive wheels. So if you put the drive wheels up front, the whole back is going to go and hit somebody. So you have to be very careful that, when you turn in place, you don't, hammer somebody on the side. But as I said, till 125 kilograms, we have some, I'll try to show you some pictures, but we have some really heavy robots that we built ourselves based on this differentially steered vehicle concept. So let me see if there's anything else. I'm going to go back to that the PDF. Here it is. And just finish up. Okay, close this. His derivation is, I don't like it, that's why I did my own. If you like it, you can follow it. But we're just going to focus on some 2 or 3 programs, so we don't really care about the derivation. But I got a sense you understood what's going on. So essentially, we showed that V is the average of the 2 velocities of the wheels, and this is where the motors are. So if you think you're not going to go any faster, you're not able to go any faster, you have to look at the motors. No point in looking at this, because there's no motor that is directly driving me. Motors are driving each of these 2 wheels. So if you feel my differentially steered vehicle is saturated, it can't go any faster, it's because these motors are saturated. So it's a kind of different way of deriving it, which I did not like very much, so I did my own. Just making sure that I've covered everything. And then we have the figure of 8 that did not show up here. Maybe we try changing the resolution. So change the resolution. Yeah. So you can go through the rest of it. Yeah. I'm going to try and put back that. because that is something my doctoral student did, my PhD student did, and I wanted to show them. This one. Oh, don't touch it. It's showing up. Now, this is something my doctoral student came up with to show the effects of dynamics. So, okay, what is a black triangle? So, most differential state vehicles are kind of shaped this way. You can make this side go forward, or you can make the pointed side go forward. The pointed side is where the caster wheel is, Whereas the drive wheels are on the broader side, you can have either one of them as the front of the vehicle. It's up to you. But I'm saying that assume that the differentially steered vehicle is parked right here, because I didn't want to draw it there because then you cannot see what's going on there. So the arrow indicates that that's where the vehicle is. So he did the figure of 8, figure of 8, just like you're doing the L, right? We can make the robot go twice around the figure of 8. What we have to do is, we go around once and then we switch omega. So when you switch omega, it will start going around the circle in the opposite direction. So it will come all the way around. And you switch omega again, it will go all the way this way. And you switch omega again, and you can bring it all the way around. Figure of 8, twice, done. Now, why are you getting, how come we don't just get the second 8 falling back on the first 8? We seem to get like 2 8s, right? But the second 8 should be the same as the first 8. Yes, if it's the kinematic model is valid. So that's why I've numbered the sides of the circles. So this is where we start. So this is the first piece, this one, the outer one. Let me put it in projection mode, but I don't want that. I don't have my mouse now. Okay. So this is 1. Watch me. 2, 3, 4, 5, 6, 7, and then 8. So you know what the explanation is for this? So initially you're stopped, right? So right wheel velocity. This is where the motors are connected. V doesn't have a motor. So V right and V left, V1 and V2, right? They are both stopped. So to go counterclockwise around the vehicle, the right wheel has to get to a higher target velocity. Both are at 0 now. But the right wheel has further to go. And I'm assuming they are the same motors. Like, not the same motors, but identical motors. You bought it from the same manufacturer. You bought 2 of them, right? So you start at 0, 0, and one has to go further than the other. The right has to go further than the other, right? So it's going to take a longer time, right? So kinematic model will be valid at each instant, but you haven't immediately got to the target velocity. You have to use the acceleration to get there. So initially they'll be keeping pace, won't they? They both started at 0. They are identical runners. So they'll be running alongside each other till they reach the lower of the 2 velocities, correct? So the initial path will be a straight line. Do you get it? You won't be on the circle. So that's why you see like a flat line here. See? They're both keeping, and then the left wheel reaches its target velocity because it has a shorter distance to go. But the right wheel has to keep going. And somewhere there you get the ultimate circle. Somewhere here it has reached the target velocity. Are you okay with that? Then you don't change anything. So everything is fine. You go around the circle, and then here you have to switch, make omega negative. So you know what that means. The right wheel was moving faster than the left wheel on the upper circle. But now the left wheel, how else do you swing this way? You have to make this wheel go faster than the other, right? It's not going to happen immediately. So till it happens, you won't be on the final circle. Till the left wheel, they are basically exchanging velocities. Do you get it? Because I'm using the same radii. If I put different radii, it's a different matter. But right now I'm using the same radii. So they have to exchange velocities. So because they have to exchange velocities, you don't get the final circle immediately. So you get this circle. So 3, everything's steady here. You know, once it reaches the terminal velocity, it's steady, 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 and then now you have to switch again. But now it's not the same switching. Initially you started from 0, 0. Now it's a switch, but it's not the same as 0 to target now. You just have to exchange velocities again. So that's why number 5 does not fall on number 1. So that's an illustration of why dynamics is important. It's quite a bit of shift, you can see, you know. It's literally you're sitting in a car and you think you're going here, but you're actually going here, right? But a human being is capable of, you know, compensating for those things. Sometimes when you build a small car and suddenly a friend says, hey, try out my car today, initially you have a little bit of difficulty, right? But you figure it out. That's what a computer is forced to do in trying to learn the model. It has to learn how the car behaves and then apply the control system. Same thing human being does. If your friend rents you like a Mercedes, you have a rich friend, then it feels different initially. Then maybe in an hour, you know, you're comfortable with it. That's the same thing. The control system, you have to learn how the vehicle moves first before the controls can be effective. Do you have any questions? Because I think we're going to stop here. I see we're getting tired. Okay. No questions? Okay. So work on the homework. I'll post the final version tonight. Ask questions next week through Teams. Don't be shy. Start early. I have to discuss a deadline. What is an appropriate deadline? Because I know you have exams next week, but we'll work with that. Yeah. So, all right. I'll see you tomorrow. Are you going to come or?